I want to start by echoing what Jose said and welcome. I think it's going to be a really fun couple of weeks. I've been very much looking forward to it, and we've had a lot of fun putting together a program that we think you'll like. So without further ado, I'm going to talk about equivariant homotopy theory. And so equivariant, and I'll try to write a lot of what I say. So equivariant is just the same thing as something like with a group action. So think of this as an adjective that can describe any number of concepts in math. I have my ordinary concept, spaces, and then I have the equivariant context, which is just spaces with a group action. So what do I mean when I say with a group action? So I'll start by just making the definition. If G is a group, and then a G space is a space X plus a map from G cross X back to X that I'll just write as follows. A point Gx is going to go to G times X. And then it's supposed to satisfy two things. The identity element in the group, which I'll always denote with the letter E, acts as the identity map on X. And then second, I want G times H times X to be G times H times X. And then you'll notice that I stressed that X was a space, and I didn't say anything about the topology of G. Often this will be implicit in the context. G could be a Lie group, in which case the topology is an integral part of, in fact, it's the Lie part of calling it a Lie group. And the cases that I'll talk most about in the next few days, G is going to be a finite group, in which case it's discrete. When I have this map should be continuous. And so in the finite group case, there's no ambiguity. It's really just a collection of maps, and for each element little g, I get a continuous map. X goes to G times X. So one of the ways I can think about this is this data is the same as giving myself a homomorphism from G into the self homeomorphisms of X. Of course, since G was actually a group, I could have just mapped into the self maps of X, and then they would necessarily be homeomorphisms because every element in G acts invertibly by this property. So I'm actually specifying a little bit redundantly, but I want to make sure that it's clear. So let me give some examples. Well, the base example are representations. So if V is a real or complex representation, of G, then V is a G space, where the action is just the action coming from the representation. I can get a few others in the same vein. I can take the sphere S to the V, and this is just the one-point compactification of V. And this, again, is a G space, where I say that G acts as the identity on the point at infinity. And if my representation was orthogonal or unitary, so if V has an inner product, then I can talk about the unit vectors in V. Those elements whose length is 1. Or I can talk about the unit disk in V. And those are those elements of length at most 1. And these are also G spaces. And this was to say that these are G spaces is that the inner product is supposed to be compatible with the action of the group. So it's one that we know from representation theory, namely the inner product of V and W should be the same as the inner product of G times V, G times W. So in other words, the group acts by isometries of the inner product space. So I wanted to mention these at the very beginning because these will show up a lot. That in many ways, these are the building blocks of equivariant homotopy theory. We say, I can understand representation theory. This is a purely algebraic problem. I want to understand this topological problem. So what I'll start to do is figure out how to understand spaces by building them out of pieces that look like these 3 groups. So that look like spheres in a representation, look like representation spheres, which are these guys. That order is confusingly important here, and then the representations themselves. If my group is sufficiently small, I can also pretty easily draw some pictures. Let's say if G is the cyclic group of order 2, then I have 2 representations. I have the trivial representation, in which every element acts as the identity, and I have a second representation, which I'll call the sign representation. And this is just the map from C2 into the general linear group GL1R, which is the non-zero elements of R, and it sends my 2 elements, E and G, to 1 and -1 respectively. So in other words, the non-trivial element acts as multiplication by -1. So if I draw a picture of, say, the 1 plus sign representation, then, well, I have the underlying vector space is just R2. Because I have a copy of the real numbers for the trivial representation and a copy of the real numbers for the sign representation. So I'll put in just my R2. But I want to include information. Namely, I want to show how's the group acting. And so I have to decide, when I'm looking at a pair of real numbers, x, y, the non-trivial element in the group sends this pair to x minus y. So now I see that points have two very different behaviors. What are the two kinds of things that can happen? Yes. Yeah.
They can either be fixed by one element or they can be reflected along the x-axis.
Exactly. I have two possible things that happen. If y is 0, then minus y is also 0. And so the x-axis here is special. And if I'm on the x-axis, the group acts trivially. That at every point here, when I apply any element of the group, it acts as the identity. If I'm off the x-axis, so if I have some other point, and then now y is non-zero, so when I take minus y, that's also non-zero, and exactly as you said, I've reflected about the x-axis. So I end up with a little point down here. So I'm doing this example to stress two things. One, here's a G-space, and I already see that points have extra data attached to them. Namely, does the group move me? And if so, which elements of the group move me? If I'm on the x-axis, nothing moves them. That they're all fixed by the whole group. If I'm off the x-axis, then every non-trivial element of the group moves them. And in fact, I can't really distinguish between either of these 2 points because I've chosen one, and if I want to remember not just points, but the points with the group action, the moment I've chosen the top point, I've also been given the bottom point because that's the action under the group. I can't separate them. So these are together two of the important parts when I want to try and understand G-spaces. So I'll just make precise what we observed here. So I'll say if x is a point in a G-space, then the stabilizer of x which I'll usually write as stab x. This is the set of those elements of the group that send x to itself. And more generally, I can always talk about the stabilizer of some subset, but this is the prototype. It's a stabilizer that sends all of the points to themselves. So here, we have two examples. If I'm on the x-axis, what's the stabilizer? The whole group. All C2 is the stabilizer from on the x-axis. If I'm not on the x-axis, what's the stabilizer? The identity. So in both cases, the stabilizer is a subgroup. Of course, I'm looking at C2, so that's not super surprising. There aren't a lot of subsets of C2, and if I have a subset of C2 that contains the identity, it has to be a subgroup. So that's not super surprising. But in fact, it's not hard to check that this is always a subgroup. And it's not hard to check because, well, I just have to check this condition. And I know that the identity is in this set because the identity times every element of my space is that element. That was the first of the two axioms that I had to satisfy. And then second, I need to know that G times H is in this set if G and H are both in this set, but that's the second axiom. So it's a fairly in fact, I just finished the verification in words. The other piece that we saw was I had the two blue dots, and then I made sure they were connected. So that's the other part. If x is in X, the orbit of X is, I'll write it as G times X. This is just all of those points of the form G times X for all elements of the group. So again, I've seen already here, when I want to understand this space, I saw that points had different kinds of orbits. Points on the x-axis were their own orbit. Points off the x-axis had orbits that looked like 2 points, and the group acted by swapping those 2 points. So the stabilizer subgroup was a subgroup of G. The orbit of X is a subspace of X. So exactly the same companion proposition is that G times X is a subspace, a G subspace of X. And these are really closely connected. So the more interesting proposition is the following one. The map that sends G modulo the stabilizer subgroup of X, so the cosets, to G times X, that sends a coset, G stab X, to G times X, is an isomorphism. And if let me give this a name, pi, and if I look at pi of G times some coset, this is the same thing as G times pi of that coset. So I'm able, with this notion of the stabilizer and the orbit, to classify all possible orbits that show up. And the classification of orbits that show up is the same thing as the subgroups that arise as stabilizers. That if you know the one, then you know the other by this. Yeah?
This isomorphism is between groups?
So if, in general, the stabilizer subgroup is not normal. So this is just a set. And this one also is just a set. Or if the group had a topology, then this would be a statement about topological spaces as well. So no, when I say isomorphism, I don't mean isomorphism of groups. I'm predicting that this kind of property, that a map that commutes with the action of G, is going to be distinguished. And so it's an isomorphism of G sets. And that's the no, that was I was being lazy there. But so I will leave to you to prove this. And if you're so inclined, we can talk about this, if you've not thought through it, at the problem session. So the proof will be an exercise. I know, I'm actually making you work. So, as was asked, this is showing me that if I want to understand maps out of this, well, any element, any orbit is of the form G times the identity coset. And so if I have this property, that pi of G times, well, any coset is G times pi of that coset, then this tells me that pi is completely determined by this property and the value of it at the identity coset. So that's it. That actually is sort of the engine that makes a lot of the kinds of computations that we're going to do work. I've reduced the problem of understanding a general map to just understanding the map at a single point, the identity coset, and then said equivariance. And I learn it everywhere else. So it's almost like magic. But I need to talk about the maps more generally. So I'll say if x and y are G sets, or G spaces, then a continuous map f from x to y is equivariant if f of g times x is g times f of x for all g in g and x in x. So there's a slight abuse of notation here. This multiplication is taking place in the G space X. It's using the G space structure on X. This multiplication is taking place in the G space Y. It's using Y as multiplication. In general, I will never stress this point again. And I'll assume that it's obvious from context. But what it tells me is this is the notion that I would come up with if I wanted to say, well, what should a homomorphism be? A homomorphism should preserve the structure that I see. What's the structure that I see? I have a multiplication by elements of the group. So this preserves multiplication by elements of the group. It commutes with it. Just as an ordinary homomorphism says that f of g times x would be f of g times f of x if I was a homomorphism of groups. It's the same setup. So the collection G spaces and equivariant maps forms a category. And I'll try to consistently refer to it as top G. So for those of you who haven't seen the notion of categories, really it's just a way to package that I have some collection of things that I want to think about, in this case G spaces, and I have some collection of maps between those G spaces that I also want to distinguish. And what I need to know is composition of equivariant maps is equivariant, and that the identity is an equivariant map. Well, talk me through that one. Is the identity an equivariant map? Sure. What would I have to check? I'd have to check that the identity on G times X, which is, in fact, G times X, is G times the identity on X, which is G times X. So it's kind of vacuously true. It's like asking, is the identity a homomorphism of groups? It's exactly the same argument. Composition, I'd also want to check. If I take F composed with F prime of G times X, well, I need to know that that's, again, equivariant. So F composed with F prime of G times X, well, this is F of F prime of G times X, F prime is equivariant. So this is f of g times f prime of x. F is equivariant. So this is g times f of f prime of x, which is g times f composed with f prime of x. So that's all I would need to know. I've justified calling this a category. And in that sense, in the categorical sense, this is an isomorphism. So it's a map in the category. The map has an inverse in the category. And I'll leave to you to write down what the inverse would look like. All right. So maps from G mod the stabilizer, or maps from G mod H into well, the orbit was an isomorphism. I can ask more generally what's happening. So I can ask, what are the equivariant maps from a general orbit, G mod H, to a general G space X? From this proposition, this is actually a really natural question to ask. Any point in X gives rise to an orbit, G times X. So I get a way to associate to every point of my G space orbits. And so I can ask, well, my G mod the stabilizer of X mapping in, that was giving me, in this collection, or from this map, a distinguished map from G mod the stabilizer of X into it. Namely, it pulled out the orbit G times X. So I would hope that general maps, G mod H into X, would also tell me information about all of those points whose stabilizer subgroups are somehow related to H.
H is a normal subgroup?
Not necessarily. Yes, H is just a subgroup. And actually, I'll try very hard to be consistent, that when I say something like, when I use the letter H or letters around H, it will always be just a generic subgroup. If I want to stress that a subgroup is normal, I'll almost always call it N. N. So N will be normal subgroups. It'll help me keep in mind too. All right, well, let's think of what an equivariant map like this looks like. So I have G mod H into X, and I just have some map F that does this. Well, again, every element here is of the form GH, the coset of H. On the other hand, just as was right there in the text I haven't erased for pi, this is the same thing as G times the identity coset, EH. So if you give me an equivariant map from G mod H into X, this is the same data as, let me also, actually, I'll write this in this way. So F is determined by F of the identity coset. Because, well, equivariance. F of G times G times the identity coset of H. This maps to, well, this one went to F of G times F of GH. But by equivariance, this was G times F of EH. So I learned everything that I would want there. I haven't quite used everything that I know yet. elements of H act trivially on the identity coset. So if H is in H, f of the coset of little h, well, this is the same as the coset of the identity. On the other hand, equivariance tells me this is h times f of the coset of the identity. So now I have completely specified it. So what I learn is that a map, a G map, from G mod H into X is the same as the H fixed points of X. So this is a set of all of those X such that H times X is X for all H in H. And the map here that identifies the two of these, so the set of all of these, I send an element F to F evaluated at the identity coset. So this isn't quite what I saw before. It's not the case that these are all of the points whose stabilizer subgroup is exactly H. That would be the ones for which I would get nice bijections from G mod H to its image. If I have a point that's stabilized by all of the group, well, in particular, it's stabilized by any subgroup. So then the G fixed points of X are also the H fixed points of X, and I learned that all of my maps from G mod H into X is just points of X again. So I don't have any information then. It does say that maps out of this is determined by H equivariant information. This space, the H fixed points of X, doesn't care that there was a bigger group that H sat in and that bigger group acted. The only condition I see is a condition on H times X is X for all of those H in H. So this is a space, and it only cares about the underlying H action, not about the G action. And so I have this dictionary that says this cares about the G space X a priori, but I learned that I don't really care about the G space X, I only care about something related to H. Category theory provides a way for me to describe this exact phenomena again. So if H is a subset of G, then we have a forgetful map functor that takes me from the category of G spaces to the category of H spaces. And I'll call this IH upper star, because I want to think of it as pulling back along the inclusion of H into G. So this is telling me maps from G mod H into X is related to information that only cares about IH upper star of X. It only cares about the H equivariant story. So to make that precise, I want to just push a little farther on this. And I want to do the limiting case. let's look at maps from G mod G into X. And I'll put a little G up here to remind us that these are going to be the equivariant maps. From G mod G into X. And so what I see is that an equivariant map, by just plugging in H is G, this is the same as the G fixed points of X. All right. Yeah. Yes. Yep. Yep. And actually, that's exactly where I'm going. So, yes. So this functor restriction actually has both adjoints. I have a map that takes me from H spaces to G spaces, and then I have another map that takes me from H spaces to G spaces. And at this point, I haven't drawn either of them. Well, I've drawn the arrows, but I haven't said what they are. This one is induction, and this one is co-induction. And I'll just write them in here because of your question. But then now I'm going to spend some time talking about exactly why and how this pattern is completely predicted by what we've just seen. Here, maps from G mod H into X, that's the same thing as H equivariant information, but then the fixed points of something, this is the same as maps from a point in. So this is the same. This was, using my new notation, G maps from G mod H into X, whereas this one was H maps from H mod H into X, viewed as an H thing. And I want to be very pedantic here and actually put in the IH upper star. Often I'll end up forgetting to do so in the future. But this is the start of what it means to say that here I have an adjunction. This is the functor IH upper star applied to X. This is the right adjoint because this is in the right slot. Here, my G mod H, this is G cross over H with H mod H. So this is the functor G cross over H applied to this, now in the left slot. And I'm saying that these two Hom objects are naturally the same. I can't distinguish between them. So let's just tease it apart a little. So I'll say that if X is a H space, then I'll define G cross over HX to be just the Cartesian product, G cross X. And then I'm going to put in a relation that says G times HX is supposed to be the same as G H times X for all H in H. It only makes sense to have elements of H act on X, but then I want to say that an element of H acting on X is the same as that element in G. So I'm remembering that H both acts on X and sits inside G, so it also acts on G on the other side. Okay, so I'll define co-induction in just a minute. I wanted to think about this one a little more. You should think of this as a kind of tensor product construction. Here I have some algebraic thing that acts. This one's a left module for it. This one looks like a right module because I'm acting on the right on G. And then I form my tensor product construction, which is just a middle linearity condition, that the action on the right is equalized with the action on the left. Just as here I'm seeing something that's related to a notion that we know, namely the tensor product in modules, this is also an example of something that comes from modules. If I want to understand what are linear maps out of the tensor product. Linear maps out of the tensor product, well, we know a bunch of different descriptions. One of the ways I can think about them is they're bilinear maps out of the two factors. So if I hold one of those factors fixed, the maps out of the tensor product are maps from that first factor into linear maps out of the second factor. Same sort of setup. Maps out of the tensor product is maps out of one of the first factors in the tensor product into maps for the second. So there's really, it's a lot that if you keep linear algebra in mind, it'll help with a lot of the topology. But now I can state and sketch the adjunction result. If X is an H space and Y is a G space, then the G maps from G cross over H X into Y are naturally the same as the H maps from X into Y viewed as an H set. I'm sorry? Oh, thank you. I have an action of G on the left here. So I'll say that G times G prime X is going to be G times G prime X. So in other words, the only way I could possibly have elements of G act is by having them act on G itself. And then it was important here that G, in this case, acts on itself on the left. H was acting on the right. So I can either act on the left and then on the right, or act on the right and then on the left, and I get the same result. So in other words, by acting on two different sides, the two actions commute. And so this formula, as I wrote it down, really takes place in this Cartesian product, but it descends to the orbits. So I can check that if I had a little h here, well, of course, I could just move that over or not by associativity. Thank you. All right, so this one I'm going to sketch again. So let's say I have a G map. G cross over H, X into Y. So what do points here look like? Points here look like equivalence classes of pairs, G comma X. But again, this is always G times the pair identity comma X. So again, an equivariant map, this one goes to F of the pair GX, so I should put it like this. Whereas this one went to G times F of that pair, identity comma X. And so again, the map is completely determined by where do pairs E comma X go. And now I'm just going to copy what I wrote there, but with the slight elaboration that I have the second factor of x. So again, I shouldn't have erased that. I'm going to now look at, well, what happens if I have an h in H and I want to look at f of the pair hx. Well, on the one hand, this is h times f of identity x, just by saying h was an element of G, so apply that way. On the other hand, the equivalence class of hx is the same as the equivalence class of identity h times x. So if I say my function specified by its values, this way. So if I define f tilde, and this is going to take me from points of x to y by a point little x goes to f of the pair identity x, then this guy, this is f tilde of h times x. This one is h times f tilde of x. So if I define f tilde in this way, then f tilde is h equivariant. So really I should have said here. Because I don't care about the rest of the G action, I would only possibly care about the H action. So given an element on this side, I've produced an element on this side. And the second exercise is show that this is a bijection. So in other words, if I give you now something over here, tell me, how do I build something over here? And one way that it's helpful is to think about this. Think about the case where G is discrete, so a finite case. Then G cross over hx looks like just a bunch of copies of x stacked on top of itself, and you put them together. I think this is actually the assembly statement that you'll be talking about. Maybe. Well, this is the joy of speaking first. I get to say what sort of things you have to do. Oh, I don't want to erase it. So what do you think the formulation of the right adjoint would be? What's the categorical property that the right adjoint is going to have? So here I said G cross over H something is the left adjoint to IH upper star. When I talk about co-induction, co-induction says IH upper star is the left adjoint to this co-induction functor. So just from that, what should I write down? What's the analogous proposition?
It maps into the imaginary function?
Yes, that when I map out of IH upper star of something, so in other words, well, when I'm in IH upper star, that means I'm in H things. Maps out of IH upper star Y is the same as G maps from Y into functions into the right adjoint. And so now I can say what this is. This is just H maps from G into X. And if you trace through, you'll get the same thing. You should again think of this as a kind of tensor product construction. The tensor product, I could either say hold the first factor fixed and then maps out of the tensor product of m and n is maps from the first factor into the maps from n into something, or I could hold the second factor fixed. Maps from something tensor m in is maps from m into the. So this is the analogous. Here's the one that I want to think of as my maps in, and then here's my sort of middle linearity kind of condition. G maps from y into H maps from G into X. So again, it's a maps into maps being adjoint to the tensor sort of construction. I'll leave it to you to check that this, in fact, is true. I'm also sweeping under the rug here, though it's not difficult. These bijections are what are called natural bijections. So in other words, if I have a map between two H spaces, that induces for me a map on the corresponding Hom objects over here, and a map on the corresponding Hom objects over here, and the obvious diagram I would write down commutes. If I have a map of G spaces from y to y prime, that gives me a map from map G, G cross over HX, y, to map G, G cross over H, X into y prime, and same over here, and that diagram also commutes. Yeah?
Say how mapping space is a G space.
So G has always two possible slots that I can act on itself on. I can either act on the right or on the left. And so in this one, one of those slots is going to be taken up by saying G is an H space. And I'll be doing left H spaces. So the left action of G on itself gives rise to a left action of H on G. But then I still have a right action of G on itself that I haven't done anything to. So if I just compose with that automorphism of G, that endows this with the structure of a G set. But another way, if I think about it as functions, if an element here is a function, then I can say G times f of x is going to be something like f of x times G. And then I have this weird swapping because of the variance that we run into with functions all the time. But, okay, thanks. All right. I think what else I want to. So let's go back. Oh, you'll see that I spent a lot of time talking about induction and not a lot of time talking about co-induction. The reason is, once we stabilize, there's no difference between the two. And that's actually going to be the big feature of stabilization. That's why we talk about stable homotopy rather than unstable. You should think of induction as a kind of disjoint union. I have G mod H copies of X. That was the image I was describing through hand gestures. That I have a bunch of copies of X, and it's indexed by G mod H. And how does the group act? The group acts by rotating the stack around according to their indices. This function object, well, function objects generically are giving me products. So as opposed to taking the disjoint union of G mod H copies of X, I take the product of G mod H copies of X, and I let the group act by rotating the coordinates around. That's exactly what this description is. And so in general, well, I mean, just count. If I take a disjoint union of a bunch of things versus I take the product of that collection of things, even if I have the same number of factors, generically the product is much, much bigger than the disjoint union. Stabilization, it provides this miracle that once I stabilize, the obvious map that takes me from the stacks in here into the product of all the copies that basically just says, it's sort of the characteristic function. It says take some element x to the function that sends the identity to little x. That map becomes an equivalence. And I don't want to write that right now, because I'm actually going to spend some time, probably Wednesday, coming to terms with exactly that. But it's why I'm not going to talk about co-induction again. So now, I haven't really used much about spaces, or anything that you've probably seen in a topology course. But at this point, I can start talking about some of the extra structure that we see, and things like, what do I mean by a CW complex in this case? Because if we learn anything in our first semester algebraic topology course, it's that spaces tend to suck, and that a generic space is really, really ugly. But CW complexes are awesome. We can actually compute with them. We have theorems that hold only for CW complexes, but they're really great theorems. And everything can be approximated by a CW complex. So we don't lose a lot of information by restricting attention to the class of spaces that we like. So let's look at those. So I also at some point need to talk about pointed versus not. So I'm going to say that a pointed G space is G space X together with a point little x in X such that, well, I'll just write it this way, a point little x that's in the G fixed points of X. So in other words, when I talk about a pointed thing, I've specified a base point, as always, but I want that base point to be fixed by the action of the group. I could try and do a more general thing, where I remember the sort of isotropy, but you don't gain a lot. So this is the one that I want to stick with. I can say that a map is pointed, a G map F is pointed if F of the base point of X, actually I'm going to just denote the base point by a star when I don't want to actually worry about naming it. So F of the base point of X is the base point of Y. So in other words, it's just as we saw in the ordinary case, I request that I send the base point to the base point. Now I can do all of the things that I did before. I can talk about induction and co-induction in the pointed context. But when I keep track of base points, I need to remember a final operation, and that's the smash product. So if X and Y are in pointed G spaces, so I'll just put a little star here to remind us that this is the same star as over there, the pointed G spaces. Then I have X wedge Y. This is the disjoint union of X and Y modulo the relation that the base point of X is set equal to the base point of Y. So I take the disjoint union and declare that I have a unique base point now. And the smash product of x and y is the Cartesian product of x and y modulo the wedge of x and y, where I map the wedge of x and y in by saying that a point little x goes to the pair x comma base point of y, a point little y goes to base point of x comma y, and the only possible ambiguity is at the base point, but then that went to base point of x comma base point of y. So this gives me a nice map. And so now my pointed induction is just G plus smash over H, where this is G itself obviously isn't pointed. I asked that my base point be fixed, and every element of the group moves, every non-identity element of the group moves every other element of the group. So G plus is just G plus a disjoint base point. And basically, all this is saying when I do this induction, this smash product, well, what would I take? I'd take G plus. So that's the same thing as, well, G and then a disjoint base point. So when I form G plus smash Y, that becomes G cross Y, disjoint union, plus my base point cross Y. And then what do? Well, I crush out everything in my base point cross Y. So that I wipe out. Well, that didn't do a whole lot. That was an extra factor. That was kind of noise that was showing up. And then the other thing I had to do was take anything in G cross the base point of Y and crush that to the base point. And again, I'm not losing a lot of information there. The base point was fixed by every element of the group. So think of this as just moving the points around, that the G cross is sort of giving me the generic ways I would move those points around. All I'm saying is that the base point is fixed always by every element of the group. So it's bookkeeping, but it's a conceptual one. So soon I'm going to work exclusively in the pointed context, and that's why I wanted to bring it up. Now I'll say what a GCW complex is. So a GCW complex, you know, I'll do a pointed one. Is a G space of the form union of other G spaces, x to the n, such that the following holds. For each n, there is a G set T sub n and maps T sub n plus smash Sn minus 1 into x n minus 1 with xn the cofiber. Really, I mean the homotopy cofiber. So I mean, I push out this includes into Tn plus smash the n disk and the whole thing gives me xn.
G set is an invariant subset. It's invariant under the action. What is it?
Yeah, so a G set is just a discrete G space. So it's just a set together with an action of G. Okay. Quick show of hands. Who's seen the notion of a CW complex before? All right. So then I'm giving you essentially the standard notion of a CW complex, but you've probably seen it done a little more attach one cell at a time. So the normal version says, start with a collection of points, and then start attaching one cells to that collection of points. Well, what's a one cell? A one cell is just a one disk, and then you tell me where do the boundary points of that one disk go in my collection of 0 cells, and then glue in my disk by just actually taking the union of this union this, but I've identified the two common images. Here I've done all of that in one fell swoop. There was nothing that said I had to say, okay, first do this one cell, then do another one cell, then do a different one cell. I could have said, these are all of my one cells. And for each one cell, this is how I attach it in. That's what this does. In this case, Tn, if there's no equivariance, so start with that point, Tn is just telling me the set of all one cells. And so when I do Tn plus smash my Sn, this becomes a wedge of cardinality of Tn n minus 1 spheres. And this becomes a wedge of cardinality of Tn n disks. So in other words, exactly what I want to glue in. I want to glue in cardinality of Tn n cells. And the best way to glue them in is to say, have them act completely independent of each other. So wedge them together, because the thing that I want is the base point should always go to the base point. That's sort of fixed. But otherwise, I don't say anything about what happens. They just all are wherever they are. It's a bouquet. The boundary of that is a bouquet of n minus 1 spheres, and each of those gets to go in wherever I send it. And so this is just each of the boundaries of my n cells should land in the n minus 1 skeleton. And then I've built it all inductively. Yeah?
I think I'm still not quite understanding this, maybe this co-fiber condition, but how do you ensure, so for each n you have a G set Tn.
Yes.
How do you ensure that the G action is compatible when you pass from Tn to Tn plus 1?
That's a great question. And that's actually hidden in this statement. So I'm glad you asked that one. Let's think about what the G now let's put in the G action to make this a GCW complex. If we understand, if there was no G action, then do we understand that this is the ordinary definition of a CW complex? I've just indexed everything differently. I said, do all of the n cells at the exact same time and put them all in. How does the group act? The group acts. So the G action here and here on these two factors, the n minus 1 sphere and the n disk, these get a trivial action. So in other words, the group doesn't, it acts as the identity. Every element of the group fixes every element in those spheres. Tn is a G set. So when I take Tn plus smash this, that gets a group action. Namely, G times a pair, little t, and then a generic element here is going to be G times T S. I'm really using the diagonal action, so really it's G times TS is G times T, G times S, but then G times S is S. That tells me that this is a G space, this is a G space, and the map is equivariant. Because if I think of the inclusion of Sn minus 1 into Dn, well, that was equivariant because it had a trivial action. But if I just wrote down this expression that when I take G times Ts and I view that now as an element here, I see that this expression still holds. So this map is equivariant. I'm going to insist, well, I have this map. The only maps in my category are equivariant maps. So by assumption, part of the data that I'm given is an equivariant map from here to here. I'm sorry? Here. Here's my, yes, here's my plus. But. So this guy is also equivariant. So x0 does get an action. And if I look at this for, I should probably say that n, or that x minus 1 is going to be something like the empty set, or, I mean, the pointed context, a point. And a point as the base point has a unique action. So then when I start to put in my 0 cells, well, I also need to figure out what do I mean by the minus 1 sphere. So I would say that that's also a point. And then it becomes an issue of T0 plus smash a point. Well, that's fine. I can understand it. Mapping into my Dn, which I would, well, this is ugly. I would want to think of that as the, yeah, I hate this indexing at 0. Maybe I'll just say T0 is my set of 0 simplices. And that'll answer the question. That'll make it even easier for me.
For the sphere, you have to also take a base point.
Yes, for the sphere, I am implicitly taking a base point. I'm choosing one once and for all, and assuming it's compatible with suspension. And then for the disk, the base point of the disk is chosen so that the map from the sphere into the disk as the boundary is pointed. Thank you. So this answers your question of how do I get a G space out of this? When I just write down, well, this is a G space, this is a G space, this is a G space. All of these are G equivariant maps. So when I write down the push out, that gives me a group action on this. Because any point in here sits in one of these two factors, and I know what the group action does on that. So I made some time at the beginning when I did those three kinds of examples. I talked about representations, representation spheres, and then spheres in representations. And here I've done just the most boring case. So Sn-1 is a representation sphere. This is the representation sphere for r to the n, where this gets a trivial action. And similarly, for the n disk, this is the unit disk in r to the n. So the question you'd probably ask is, why did I throw away this huge amount of structure that I have, namely all of the representation theory of G? There are many, many more representations than trivial representations, so why am I not worrying about them? Turns out this is strong enough that if I instead build anything where instead of this trivial sphere, I use the unit sphere in a representation, and instead of this trivial disk, I use the unit disk in a representation, I don't get a more general class of spaces. That every space I could get using non-trivial representations here is also in this collection of spaces. Yeah. That's exactly it. That, well, I can, any of the, I guess maybe the proposition, which is essentially what you said, that the sphere and disk are GCW complexes. And if you think, let me just justify that for a single one. The one where I actually drew the representation as a G space. So let's think about how to build a GCW structure on the unit sphere, on the unit disk, and on the one-point compactification. So let's say this is the origin, and then here's my unit sphere. And actually, I'll just ignore most of the stuff around it. All right, so talk me through. Let's look at the actual sphere. Describe for me how I would view this as a GCW complex. So what do you think I want to take as my 0 cells? Plus or minus 1. I have 2 points in this that are different. I need to leave this one with me. This one and this one, they're fixed. And in fact, these are all of my fixed points. So I'll start with those. And so that gives me just a base point, disjoint union, another base point. Base point, disjoint union, some other point. Minus 1. And what's the G action on this? It's trivial. We already said that these 2 points are fixed by the action of the group. So now what do I want to do? I want to say, what are the 1 cells that go in? What do you think the 1 cells are going to be? So I'm not including this middle line. But yeah, I have this guy. So if I'm just building this as a CW complex in spaces, I have this one. And then I also have this one. So that looks like 2. How does the group act on those 2 1 cells? It swaps them. So the group's taking this top 1 cell to that bottom 1 cell. So in other words, if I think of my yes. Yeah, it's the one that I've done before, the CIMAT 2 action. So the set, the non-equivariant set of 1 cells that I'm looking at is a set of 2 points, but the group's acting by swapping those 2 points. So I'm going to glue to this a copy of the group action, C2 plus, so that namely 2 points. Then I'm going to smash it with a 1 cell. And then what does the group do? Well, the boundary of this is C2 plus smash the 0 sphere. So in other words, when I have the C2 plus, that's saying everything inside's pointed. So we can successfully ignore that because it's just saying do everything in the pointed context. So when I do C2 cross the 0 sphere, well, this is really telling me I have a C2 for the top, an S0 that's the boundary of the top 1 cell, and an S0 that's the boundary of the bottom 1 cell. And if I know how I'm attaching the top 1 cell, then I know how I'm attaching the bottom 1 cell, because equivariance tells me the bottom 1 cell is just the group action on the top 1 cell. How is this top cell attached? It said take the base point to the base point, take the non-base point to the non-base point. So if I wanted to be more pedantic and actually write out exactly what's happening here, then the map I have is supposed to be C2 plus smash the zero sphere. This includes into C2 plus smash the one disk. And then the map from this to the zero skeleton, which is in fact just the zero sphere viewed as disjoint of non-trivial point, disjoint union base point. This is something induced, namely this is of the form C2 plus smash over the trivial subgroup with the zero sphere. So an equivariant map out of this is the same thing as a map from the zero sphere to this zero sphere where I've forgotten all of the group action. So by the adjunction that I described, this is the same as a map from the zero sphere to forget down to the trivial group, which is just the zero sphere again. And the map's the identity. So from this perspective, it's actually very, very easy to write down cell structures for all of the things I would look at. I just do this. I say, I write down all of the cells that I would need. So if I try to, oh, I'm over time. So I'll keep going. I write down all of the cells I need, but I remember the group should just permute the cells around. It shouldn't do anything in a particular cell. It shouldn't move a single cell to itself. It should actually just permute them. It should swap the cells around. And if I write down a cell structure for the underlying space where the group just permutes the cells around, then that is a GCW cell structure. And this dictionary actually lets me just say that full stop. I don't have to worry about attaching cells. Yeah?
So when you say permute around, you're not requiring it to be Fourier transitive or something.
I'm not.
You're just not.
I'm saying that if you give me some cell and I look at the group action on it, then it's just a homeomorphism onto some other cell. But that if it takes it to itself, it's the identity, not a self homeomorphism. Otherwise, I get some. Well, then it's impossible to say whether it's the identity or not. It's just actually moving it to some other one. That's all I'm saying. All right. So I'm sorry I ran over. I'll try not to tomorrow, but I wanted to make sure to finish that picture. Thank you.